Sam Schmidt, Ryan Pelikinis, and Paul Blanchard present the Five-a-Tron 5000. Insert 25 cents for a high five.
Got it. Newton's first law of motion. This point in the project shows Newton's first law, that an object in motion tends to stay in motion, and that an object at rest tends to stay at rest. On the air hockey table, friction is very low as the puck flows along on a curtain of air, just like a cart on an air track would. When a force begins to move the puck, it moves at a near constant velocity and stays in constant motion until it hits the goal on the other side. Thus, it stays in motion until acted upon by the force of the opposing goal stopping it. This is also seen in the domino tracks. The dominoes stay at rest until they are acted upon by an outside force, which is another domino. Following Newton's law, they will not fall until they are acted upon by an outside force, be it someone's finger accidentally brushing up against it or another domino striking it. Newton's second law of motion. The ballista and the Nerf gun both portray Newton's second law, that force equals the mass of the object times acceleration. In the ballista, the firing mechanism imparts a force of 4.72 newtons onto the blocks, which weigh about 0.35 kilograms. Therefore, they accelerate forward with an acceleration of 13.5 meters per second squared, for about 0.4 meters. The Nerf gun accelerated the Nerf dart at a much higher acceleration because the dart has a much smaller mass. These two different forces show that with more mass there is less acceleration, and with less mass there is more acceleration, which is consistent with the equation for force, F equals ma. Newton's third law of motion. Newton's third law, that every action has an equal and opposite reaction, is shown in the actual firing mechanism of the Nerf gun. To fire the gun, a weight rolls down a ramp and pulls on the trigger. However, the weight also stops halfway down the ramp after the gun has been fired. This means that for as much as the weight pulls down on the trigger also pulls back on the weight, showing that for every action there is an equal and opposite reaction. The conservation of energy is portrayed in many aspects of the Rube Goldberg. The first is the elastic collision between the two bouncy balls. While it is not completely elastic, it is fairly close. In an elastic collision, both energy and momentum are conserved. This means that the energy the two balls have before the collision is the same amount of energy they have after the collision. The lighter ball that was at rest started with a velocity that was less than the original velocity. The heavier yellow ball that was already in motion ended with a velocity that was much less than both of the other velocities. The equations for elastic collision support this result, and the kinetic energy in the first ball is about equal to the kinetic energy of the two end balls. Conservation of energy is also portrayed in the marble rolling down the marble track. In the beginning, the ball has no velocity, so all of its energy is stored as gravitational potential energy, which is mgh. However, throughout the run, the marble picked up speed and kinetic energy, while losing potential energy, and ended up with enough energy to knock down the block at the end of the track. However, the total energy of the system remained the same. It was conserved. While the energy changes forms, the total energy did not change. This point in the reaction shows the conservation of momentum because it is a completely inelastic collision as the two trains stuck together after the collision due to a magnet. Therefore, momentum is conserved, but energy is not. This is because before the trains rolled down the hill and gained extra velocity, the momentum, which is P equals mv of the two trains, before the impact was the same as the momentum right after the impact. Since the one train started at rest, this means that the two connected trains had the same momentum as the first train did by itself. This is evident as the train had more velocity before it hit the second train than it did after it hit and combined with the second train. Because the mass increased after the collision and the velocity decreased, total momentum, which is mass times velocity, was conserved.